Okay, so I just covered all of my notes with a keyboard. So last time we talked about groups, which are just sets that have been given some extra structure in the form of a binary map. And we saw that in contrast to sets, the classification of groups was actually quite complicated. So somehow this extra structure made this problem much harder. Okay. So today we will fearlessly trek on and add even more structure to a group. And in a delightful twist, what we'll see is that the resulting classification problem is actually really easy. So let me define for you what a vector space is. So a vector space is an abelian group. So abelian means commutative. Instead of calling it G, we're going to call it V. So it's a group and the operation is addition. Uh, well, vector addition. This is equipped with a scalar multiplication. So it satisfies all of the properties of a group with respect to this addition operation. And it's equipped with a scalar multiplication, which is a map, which takes, I guess I'll denote it by this dot. This is going to look weird, but it goes from a field, which I'll call K, and a vector space, back to the vector space. Okay, so here K is a field, and we don't really need to know what a field is. So I won't explain it just so I don't have to explain yet another algebraic structure. What I'll say is we will only consider two fields that you're familiar with. K equals R or C. Okay. So we'll only consider vector spaces over the real numbers or the complex numbers. Another option you have available to you is the rational numbers, which are also a field. Quaternions, I believe, are not a field. No, they're a division ring. Okay, I don't remember what kind of structure the quaternions are, but it's irrelevant. So we have this scalar multiplication, and it has to satisfy four properties. So the first is that A times B times V is equal to A times B times V, where A, B are in our field, and V is in our vector space. So this dot here is denoting the scalar multiplication. So B times V gives me another vector, and so I can do another scalar multiplication. This A times B here is the multiplication inside of the field. So this is multiplication of real numbers or complex numbers. Okay, we need the existence of an identity element, multiplicative identity element, which we'll call 1. So the real numbers and complex numbers certainly have 1. And then we need A times U plus V. We need this to be distributive. So again, A is in K and U and V are in V. And finally, we need to be able to distribute the other way. Okay, so a vector space is a group with this extra operation that allows you to do pretty much everything you would want to do. other than multiply vectors. Okay. So by now, hopefully we all know the drill. What we want to do is we want to classify these things, and so we need some notion of equivalence or isomorphism between the vector spaces. So with that in mind, what we should do is define a map, and in particular a linear map. I'll call it capital Phi, from some vector space U to another vector space V. This is a map satisfying two properties. So A, phi of U1 plus U2 is phi of U1 plus phi of U2, and B, phi of some number times U is equal to K times phi of U. So this is what it means for math to be linear. Here, K is something in our field. So I should maybe say K is in K, and also U1, U2 are in the vector space U. Okay, so if phi is a bijection, it is called an isomorphism. So this word keeps popping up in different contexts. So maybe we should say an isomorphism of vector spaces, just to clarify. But usually we just say isomorphism. Okay, so property A should look maybe a little familiar. All this is telling us is that phi is a group homomorphism. Okay. So remember the group operation that sits inside this vector space is this vector addition. Okay. So if we want two vector spaces to be the same, we better preserve this group structure. Okay. And so we have the homomorphism property here. And now we have this extra scalar multiplication operation. We want to preserve that too. And so we require that multiplying by k beforehand is the same thing as multiplying by k after. Okay, so property B just preserves that new scalar multiplication structure that we introduced. So finally, we seal the deal by requiring that phi be a bijection so that the underlying sets are isomorphic. So bijection gives me equivalent sets. Homomorphism gives me equivalent group, the binary map structure on the group, and property B here gives me the equivalence of the scalar multiplication structures. So if I have all these things put together, then I have isomorphic vector spaces. Okay. So here is an important example. It's one that we've probably all seen before, which is Rn, which is the set of all n tuples of real numbers. Right, so all these lists of n real numbers. And so this is a vector space over the real numbers. So what I mean by that is that this field is R. So the scalar multiplication is related to the field of real numbers. And let's see, the addition and scalar multiplication are defined component-wise. What I mean by that? What I mean is if I have two elements of Rn, the way I add them is component by component. So this is x1 plus y1 through xn plus yn. Okay. If I have a scalar, so something for my field, and I want to multiply it by a vector in Rn, I do that component-wise as well. This is a times x1 through a times xn. Okay, so you put all this together, and what you get is a vector space. So you can check all the axioms if you like. There are too many for me to do right here, but it's true, I promise. Another example is Cn, which is a vector space over C. This is Ci, C. This is a vector space over C. So you define the addition and multiplication the same way, just component-wise, just like we did before. But note that it is also a vector space over R. So we can also do Cn, but as a vector space over R. Okay. Why is that? Because a real number times a complex number is still a complex number, right? I can't do Rn over C because a complex number times a real number is a complex number, and so I won't, my result won't sit inside of Rn anymore once I multiply it by I, for example. Okay. So where do we go from here? Well, we want to classify these things, and one notion we're going to need is the notion of a basis. So first, let me tell you what it means to span something. So given a set of vectors, let's call them v1 through vm, the span of these vectors is the set. So we'll call it span v1 through vm. And the way it's defined is it's the set of all linear combinations of elements in that set. So the ki here are elements of our field, which is real numbers or complex numbers, and vi is something from our vector space V. Okay, so if U sits inside of this set, we say U is spanned by V1 through Vm. Okay. So if given any element of U, I can write it as a linear combination of elements of the set here, V1 through Vm, then it's spanned by that set. Okay, so it's useful, if I have a vector space, it's useful to know a set of vectors would span it, right? Because then I can write any vector as just a linear combination of this finite number of vectors. I should say that I'm dealing with finite dimensional vector spaces today. Okay. Here's an example. You can take the set 1, 0 and 0, 1. And this spans R2. How do we know that? Well, anything in R2 looks like x1, x2. Okay? And we can decompose this as x1, 0 plus 0, x2, which is x1 times 1, 0 plus x2 times 0, 1. So an arbitrary element of R2 is now written as a linear combination of 1, 0 and 0, 1. Okay, great. So this thing spans R2. So another property that we'll need is linear independence. Ooh. Okay, a set of vectors v1 through vm is called linearly independent if k1, v1, so a linear combination of these vectors, whenever it's 0, if that implies that k1 through km are all 0. So let's return to our example. Let's take this set 1, 0 and 0, 1, which sits inside of R2. We already showed that it spans R2. Now, is it linearly independent? The answer is yes. If I take some arbitrary linear combination, so k1, 1, 0 plus k2, 0, 1, and I set it equal to 0, can I show that this thing, well, first I should clarify, 0 in R2 is the pair 0, 0. This is the identity, the additive identity in R2. So what we do is we add up this side, we get k1, k2 is equal to 0, 0. And sure enough, this implies that k1 is equal to k2 is equal to 0. Okay, so therefore, this set, let's call it S. S is linearly independent. Okay, so that brings me to one more definition. If you have both of these properties, so if let's say S is a linearly independent.
I had a question.
Go for it.
So I understand the way you define linearly independent, but I've never seen it done like that before. Is that the base, like the standard way, or are there like multiple equal ways?
This is the way I've always seen it. What way have you seen it before?
Maybe I'm just misremembering, but I thought, I mean, it's the same thing, but I thought it was like if there's one vector and it's part of the set, it was made from this basis.
Yeah. So it is the same thing. So if you have so linear independence is telling you that you cannot build any vector from your set out of just the other vectors, from your set, right? So it's independent from them in that sense. So yeah, that intuitive way to think about it is also correct. Yeah.
Can I make a remark here?
Yes.
In fact, it's easier to define what is linear dependence.
Indeed.
Okay. It means you can write one of the vectors as linear combination of the others. and then linear independence is you can't.
Yes, exactly.
It's
And,
yeah.
and it turns out that this definition I've given here is just exactly equivalent to that.
Okay, thank you.
Okay. So if S is a linearly independent set which spans a vector space V, then S is called a basis for V. So the idea is that if you have an element of a vector space V, what you can do is you can write it as not just a linear combination of some subset of vectors, but also a unique one. So this decomposition into a linear combination of these basis elements is in fact unique. Okay. So maybe I should clarify, the basis itself is not unique. There are many bases for a vector space. But once you have a basis, the decomposition of the vector in terms of that basis is what's unique. Okay. So example, we already have one. Well, I can just point up here. This example up here, we already showed that this set spanned R2. We showed that it was linearly independent, and so that implies that this thing is a basis for R2. I should also say that the order of a basis for V is called the dimension of V. So R2 is two-dimensional because it has two basis vectors. Okay, so there's a fact that I won't prove because there's too much to get through here. The dimension of a vector space is independent of the chosen basis. Okay, so it doesn't matter what basis you're in, they all have the same number of elements. Okay. And that number is the dimension of the vector space. So this is a well-defined concept. Okay, so it turns out that's all we really need to understand the classification of vector spaces. Well, at least the finite dimensional ones. So let V be a finite dimensional vector space over the field K, which we're taking to be R or C. Then this vector space is isomorphic to Kn for some n. Well, in particular, maybe I shouldn't say for some n, it's for n equal to the dimension of V. So proof is not too hard, so maybe we'll give it a go. Let V1 through Vn be a basis of V. And we'll let E1 through En be a basis of Kn. Okay. So we need to define a map which is linear and bijective between V and Kn. So we'll define a map phi from V to Kn by sending phi of Vi to Ei. And we get linearity for free by just extending this. So what I mean by that is if I have some linear combination of vectors here, define the result to be the correct linear combination on the right-hand side. So if I have phi of A V1 plus B V2, I want this to be A phi of V1 plus B phi of V2. So we're just going to define the map that way, right? And we get linearity for free. Okay, so phi is linear by construction. All we have to do is show that it's bijection. So for injectivity, we can take, so we say suppose phi of u is phi of v. We have to show that u is equal to v. Well, we can write v as some linear combination of the basis vectors. And we can do the same for u. Notice the basis vectors are the same, but the coefficients are what's different. And now, what does this assumption imply? Well, we define this map to be linear by construction. So phi of u equals phi of v is the same thing as saying d1 phi of v1 through dn phi of vn is equal to c1 phi of v1 through cn phi of vn. So you just apply phi to v, apply phi to u, use the linearity property, and you get this immediately. Okay, so what is phi of v1 through vn? Well, that is, we define that to be e1 through en. And e1 through en are a basis for kn by assumption. So we can use that linear independence of the basis. We could get this immediately from one perspective by saying, okay, well, the decomposition of a vector is unique. So if these are equivalent, then all the coefficients must be the same, right? If we want to use the definition I gave, we would just subtract one side to the other. So if we subtract the right-hand side on both sides, then we get this equation here, and we know that since this thing is a basis, it's linearly independent, and so that implies that d1, well, in general, di minus ci is equal to 0. Definition of linear independence. And so di is equal to ci for all I. What does that mean? That means that the vectors we started with, u and v, are the same. Okay. And that's injectivity. So therefore, phi is injective. So the fact that this map is injective just follows from the fact that E1 through En is a basis, and what we did was map a basis we started with to this new basis. Okay, surjectivity is even easier. Let W be some arbitrary vector and Kn. Okay. the question is, can we write W as phi of V for some V? And yeah, of course we can. So the correct definition of V is K1 V1 through Kn Vn. If we apply phi to this, what do we get? We get phi of V is K1 phi of V1 through Kn phi of Vn, which is K1 E1 through Kn En, just by the definition of phi. And this is our W. Okay. So can we write W as phi of something in V? And the answer is yes. You define V this way and you get W. And so this implies that phi is surjective. Okay, so phi was linear by construction. We just found injectivity and surjectivity. That means it's a bijection. It's a linear bijection. That's an isomorphism. So therefore, phi is an isomorphism. And so V is isomorphic to Kn. Okay. So this is really nice. Any vector space, any finite dimensional vector space is isomorphic to Kn, where K is just the field that it's a vector space over. Okay, so at least for the case of finite dimensional vector spaces, the classification over R and C is really quite nice. Everything is isomorphic to that very standard example of Kn. And to distinguish between vector spaces, all we have to do is just compute the dimensions of the vector spaces. So just like with sets of infinite order, vector spaces of infinite dimension are not necessarily isomorphic. So this classification fails for infinite dimensional vector spaces. So I won't go into that. Steinberg does not. And I don't think that we will deal with too many infinite dimensional vector spaces, but I'll introduce them as we go. Okay. What do we do from here? Well, there is a very useful additional structure you can put on a vector space. So it's an inner product. The inner product on a vector space is a map, which we'll denote like so, which takes two vectors. We put the vectors here and here, where these two dots are, and gives us a complex number. And it has to satisfy, or I'm just going to write all the for alls right from the start. For all V, W, I'm going to need a V1, a V2, V, and C1, C2, and C. Okay, so it needs to satisfy three properties. We need that C1, V1 plus C2, V2 inner product with W is C1, that's a C, C1, V1, W plus C2, V2, W. So it's linear in the first component. Right? If you're a physicist, I believe the convention is the other way. It's linear in the second component. Right? So if you have your bracket notation, well, actually, yes, yeah. So if you're a physicist, then the convention is usually the other way, and it's just a convention, right? It doesn't matter. So So we're gonna go with the left-hand convention here. That's what Steinberg uses. And whatever convention you pick, the other component will be, I forget the name for this. It's not skew, it's conjugate symmetric. Sorry, conjugate linear, I mean. Okay, whatever it's called. So we require this property here. So if we take the inner product but in the opposite order, then we pick up a complex conjugate. So this symbol is the complex conjugate. So if anybody is unfamiliar with complex analysis, this is just you take all the i's in your complex number and make them minus i's. Okay, so what I was trying to say earlier is that this second component here for us, or for a physicist, the first component, will pick up a complex conjugate when you pull the constants out. So it's not linear, it's conjugate linear.
Is it Hermitian? Hermit symmetry?
Don't know if that word gets used. The only time I hear Hermitian is in the context of Hermitian conjugates, which is for operators. Right?
Okay.
Yeah.
Okay.
Okay. If we take the inner product of v with itself, it should be greater than or equal to 0. And it's equal to 0 if and only if v is equal to 0. Okay, so if you have a vector space and you give it this inner product, right? So you just tack on one more thing to it, then what it's called is an inner product space. So if you have vector space, which is a set with addition, with a scalar multiplication, and now if you also give it this inner product, this is an inner product space. Okay. And one more thing, just a small remark. Given an inner product, you can always define a norm. Get a norm for free. So the norm of v would be the square root of the inner product of v with itself. So the other way is not true in general. You have to satisfy what's called the parallelogram law in order for it to hold. But, if we need that later on, I'll talk about it. Okay, so just as an example, when we define something, we should usually give an example. So the standard inner product on Cn is called the standard inner product on Cn. What is this? Well, if I'm given two n tuples of complex numbers, this is defined to be the sum from I equals 1 to n of AI BI complex conjugate. So you can check that this thing is indeed an inner product. I'm not going to do that, but it's a nice little problem. And speaking of problems, here are a couple more that are important, but I don't have time to do. or I think that it would be nice exercises. So the Cauchy-Schwarz inequality says that the magnitude of the inner product of V with W is less than or equal to the norm of V times the norm of W. So V and W are some elements of a vector space here. And we also have the triangle inequality. Which says that the norm of V plus W is less than or equal to the norm of V plus the norm of W. Okay, so if you don't know the proofs of these, then I suggest you look them over. They're good ones to know. Okay, here's a definition. Now that we have an inner product, two vectors, V and W, are called orthogonal if the inner product of V with W is equal to 0. Okay, so we can extend this notion to an entire set, right? If all of the elements in the set are mutually orthogonal, we just call the set orthogonal. If they have the additional property that the norm of each element is 1, then that set is called orthonormal. So orthogonality plus norm equals 1. So unit norm means orthonormal. Okay, but here is a nice result. Orthogonal sets. Let's call one V1 through Vn are linearly independent. The proof is short and sweet. So how do we show linear independence? Well, we suppose that we have a linear combination of the elements in our set, and it's equal to 0. And what we have to do is we have to show that C1 through Cn are all 0. Right? How do we do that? Well, we can take the inner product of both sides with an arbitrary vector in the set. Let's call it Vi. So inner product of 0 with Vi is going to be 0. So we can start with our 0 here. And then on this side, what we have is the inner product of Vi with C1 V1 through Cn Vn. So again, this 0 came from inner product of 0 with Vi. So what is this? Well, maybe I should have done it the other way, because I'm doing the physicist convention now. Okay, let's swap this around so I don't have to deal with any conjugates. Okay. So we still get 0 over here. And now I can pull out my constants, distribute some things. Okay. And now I use the orthogonality of the set. Okay. So that means that everything is mutually orthogonal. So Vi is Vi inner product with Vj is always 0 unless I is j. So the only thing that survives here, all of these inner products are 0 except for the ith one. Okay. Wow, that looks like an E again. Okay. There we go. So I have that 0 is equal to Ci, Vi, Vi. And now I know that this thing is going to be, I need an additional assumption here, actually. I need these vectors to be non-zero. So if these vectors are non-zero, that means this inner product here, inner product of vi with itself, is positive. It's greater than zero. So the only way for this thing to be equal to zero is if ci is equal to zero. But I was arbitrary, so this is true for all of the I, all ci. So this implies that C1 through Cn are all equal to zero, and so our set is linearly independent. Okay.
I had a question. This might be sort of dumb, but how do we know what VI, the inner product of VI and VI is?
Okay, so let me find it. The definition of our inner product was that it's always greater than or equal to zero when you take the inner product with itself, unless v is zero, in which case the inner product of itself is, oh wait, sorry. If the inner product is zero, that implies that v is zero. Yes, okay. So we assumed that v was non-zero, so this is not the case that's going to happen, right? And so the only case left is that inner product of v with itself is positive. And so what I can do here is I can divide by the vi because I know it's not zero, right? I don't care what it is. It's not zero. And so I get ci equal to zero. Okay. So note that if v1 through vn is a basis for an inner product space, and v is equal to the sum from I equals 1 to n of ci to c vi, then actually we can just write v as the sum from I equals 1 to n of the inner product of v with vi times vi. So in other words, this ci is equal to the inner product of v with the basis vector vi. So how do you show that? Well, you can just take the inner product of both sides here with v, and what will fall out is this equality.
I think this only holds if v1 through vn is orthogonal.
Yes, you are correct. In fact, it doesn't need to be orthonormal. I don't think it needs to be normal. No. Okay. Yes, thank you. Okay, we will make frequent use of the following vector space, which maybe many of you haven't seen before. It's going to look a little weird. Given a finite set X, define another set. We're going to call it C with an X and a superscript. Functions from X to C. Then this set is a vector space with pointwise operations. what do I mean by that? I mean that if you have f, function f plus a function g evaluated at x, this is the same as f of x plus g of x. And what do I mean by scalar multiplication? Well, this is just c times f of x. Okay. Now, for each x in our set x, we can define a function delta x from x to c so that it lives in this set. We can define it by delta x of y is equal to 1 if x is equal to y and 0 otherwise. So this is the usual Kronecker delta, right? Except, well, if x is a finite set, then you can always label it 1 through n. So yeah, it's the Kronecker delta. Okay, now, maybe before this, I should have defined my inner product on this space. So we'll come back to this in a moment. We can define an inner product on Cx the following way. The inner product of the function f with the function g is the sum from, over x in our set x. So remember, there are finitely many of these things by assumption. F of x, g of x bar. So this bar is the complex conjugate once again. Okay. So this thing is an inner product, and the set of all delta x such that x is in x is an orthonormal basis. Orthonormal basis. So that means that all the delta x's are mutually orthogonal, and the norm of a delta x is always 1. Okay. So in particular, this tells us that, I don't want to lose this yet. In particular, this tells us that the dimension of this vector space is equal to the order of x. Okay. So maybe I should say a little more here about why this thing's an orthonormal basis. We can check this. It's pretty quick. So if you take inner product of f with delta x, then this is the sum over y and x of f of y delta x of y. Now delta x of y is 0 except for when x equals y. So the only term that survives is f of x. Okay. Now, let's see. Oh, sorry. This is not what I had planned, sorry. I went too far in my notes. Okay, sorry. So to show that this thing is an inner product, is a orthonormal, if that this thing is an orthonormal basis, what we're trying to do, we need to plug in a delta x and a delta y in here. Okay. So what do we get? Delta x, delta y. We can, let me do it the other way. So I can use this formula. From this formula here, what do I get? I get, let's do this again. So y and x, delta y of y, delta x of y. And so, yes, okay. The only term that survives is when x is equal to y, and then we get delta x of x twice. And delta x of x is 1, and so this is equal to 1. Okay, so orthonormal. If x is not equal to y, then we're going to get a 0. Okay.
Can I ask a question?
Yes.
The y you sum over is the same y as the y of the index of delta y.
Have I done something bad? Yes, I have. Thank you, Crystal. We need another letter here. So this should be z. This should be a z. So the only term that survives is when x is equal to z and z is equal to y. And so these conflict with each other if x is not equal to y, but they agree if x is equal to y. Yes. All right. We've done it finally.
Thanks.
So. Okay. So the point I was trying to get to over here is that since the inner product of f with this basis vector delta x is f of x, this tells us that f can always be written as the sum over x and x of f of x delta x. Right. So this comes from our decomposition of an arbitrary vector as the inner product of f with the basis vector times the basis vector. Okay, now that I've thoroughly confused us all by skipping through my notes, maybe we'll move on. Okay, so let W be a subspace of V. So that just means that it's a subset of V, which is a vector space in its own right. The orthogonal complement of W is another subspace of V, which is denoted W with this symbol up here, which is usually pronounced perp. So this is W perp. This is the set of V and V such that the inner product of V with W is 0 for every W in that subspace W. So it's the collection of all the vectors in V which are orthogonal to every vector in W. So another problem. This one's simple, but I won't do it just for time's sake. Show that this is a subspace. Okay. So what I will do is I will prove to you the following very useful proposition. Let V be an inner product space. And let W be a subspace. Then there is a direct sum decomposition. V is W direct sum with W perp. Okay, so what does it mean to be a direct sum? It means that V can be written as, so every element of V can be written as an element of W plus an element of W perp. And moreover, the intersection of these two subspaces is just the 0 element. Okay, so this means that V is W plus something and the orthogonal complement, and the two subspaces their intersection is the 0 vector. So here's the proof. Let W0 be in W intersected with W perp. What we want to do is we want to show that this W0 it has to be equal to 0. Okay, so the fact that W0 is in here means that it's in both W and W perp. If it's in W perp, that means that W0 is equal to 0 for all W in the subspace W. The definition of being in W perp. In particular, that means that W0 is equal to 0. But by the definition of an inner product, this only happens when W0 itself is equal to 0. Okay, and that shows that the intersection is just the 0 element. The only thing that can exist in there is 0. Okay, so therefore W intersect W perp is nothing but 0. Okay, so now we have to show that an arbitrary element of the vector space V can be written as an element of W plus an element of W perp. Okay, so we're going to need a basis for W. Let W1 through Wm be, do I need anything special here? I think I need this to be an orthonormal basis. And let V be an element of V. So you can ask the question, how do I know this orthonormal basis exists? It's guaranteed to us, well, a basis always exists. We can start with one vector and keep adding on linearly independent vectors until we span the whole space. And we get the orthonormal property from what's called the Gram-Schmidt procedure. I won't go over that, but it's a procedure for obtaining an orthonormal basis from a basis which is, I believe it starts from just a basis. I don't think you need to assume orthogonality. Okay. So this thing does exist, and now let's define what I'll call V tilde. And this is going to be the projection of V onto the subspace W. Oh, that's a comma. Okay, well, then V is equal to V tilde plus V minus V tilde. And we look at this and we say, okay, this is a linear combination of the basis vectors of W. And so this thing must be in W. So I've got the first part. All I have to do now is show that V minus V tilde is in fact in W perp. Okay? And then what I have is something in W plus something in W perp. Okay. So let's do that. So we have that V minus V tilde inner product with Wi is equal to V inner product with Wi minus V tilde inner product with Wi. And remember, we can expand that V tilde out. That V tilde was, this is going to be a little messy, but V with W1 through V with Wm. and we're inner producting with wi. And now what I can do is I can use the linearity in the first component to move all of these inside inner products out. So I get V inner product with W1, and I'm left with W1 inner product Wi. And we keep doing this all the way down to V inner product with Wm, and then that's Wm inner product with Wi. Okay, so since we're assuming that the basis was orthonormal, which we can do by the Gram-Schmidt procedure, all of these W somethings inner product of Wi will be 0, except for the case where this first guy is Wi. And in that case, the inner product of it with itself is 1 by the orthonormality assumption. So this is V inner product with Wi minus V inner product with Wi inner product with itself. This thing is equal to 1. So we get VWI minus VWI, which is 0. So that shows that this V minus V tilde guy is orthogonal to all of the basis vectors, right? We didn't specify which I, so it's true for all of them. And if you're orthogonal to all the basis vectors, you're orthogonal to every vector in the space, right? So that implies that V minus V tilde is in W perp. And that's it. So we decomposed V as V tilde plus V minus V tilde. This is in W. This is in W perp. And V was arbitrary, so that tells us that V is equal to W plus W perp. And we already showed that the intersection of these two things was just the 0 element. So in fact, the sum is direct. And so that proves it. Okay. So, all right, let me try to speed things up a little bit. This speed run of linear algebra wasn't very speedy. Okay, so in quantum theory, we care about a very particular kind of linear operator. It turns out that a wave function evolves according to a unitary operator. Right? This is the reason why in quantum computing, you quantum computing people, all of your gates are unitary operators, right? Because you're trying to evolve a quantum state in time. So the only way you can act on it is with a unitary operator, unless you're trying to measure. Okay, so for this reason and for other reasons, we should define what a unitary operator is. So a linear operator, U in GL of V. So this is it's actually a group. It's a group of all invertible maps. I should say linear maps. From V to V. So it's called the general linear group on V. So linear operator U in this group is said to be unitary if the inner product of U acting on V with U acting on W is equal to the inner product of V with W for all VW in our vector space. Okay, so this definition for my physicist friends is probably not what you've seen before. Right? You've probably seen the definition U dagger U equals the identity, and these are actually equivalent to each other. I think I'll show that in a moment. But first, let me make it possible for us to talk about the permission conjugate adjoint or Hermitian conjugate of a linear operator, I'll call it T, is its unique linear operator T star, or if you like, T dagger. I'm not sure which one I'll use. I'll probably use them interchangeably. The reason is I'm used to using T dagger, but Steinberg uses T star. So I reserve the right to use both. Okay, so satisfying T V W is equal to V T star W. Okay, so uniqueness of this operator follows from what's called the Reese representation theorem, but I won't go into that. Anyway, so the point is that there's a unique operator satisfying this equation, and that's how we define this adjoint or the Hermitian conjugate. So if you, once again, are a physicist doing quantum theory, then you know the matrix definition of Hermitian conjugate, which is that it's the conjugate transpose, right? So these definitions are equivalent to each other. Well, maybe I should also give a caveat. In an infinite dimensional setting, these things may not or really aren't the same. Okay, anyway, a linear map T, so T is called self-adjoint. D, self-adjoint or Hermitian. If T is equal to its adjoint. Okay. Okay, so these operators are nice. So are unitary operators. The spectral theorem tells us that they can, well, and the matrix representation of these operators, the spectral theorem will tell us that these things can be diagonalized. But, okay, all right. I gotta move on. So back to my point. So this definition of unitary here is equivalent to the one where we say U dagger U is equal to the identity. And that's not hard to see. So if you have UV, UW equal to VW for all VW and V, then that means that V with U dagger U W is equal to VW, again, for all VW and V. And since this is true for any old V and any old W, that implies that U dagger U is the identity. And you can do this a similar way. So you would move the U over here to this side, and that'll give you the other direction as well. Now, the reverse direction is even easier. So if you have this property, then UV is equal to UV, is equal to V U dagger U W, and then that's the identity, and you're done. So these things are in fact equivalent to each other. Okay, so at this point, I have to tell you about some important concepts coming from linear algebra, and then we'll be done. we can finally move on to representation theory. Okay, so first thing is the kernel of a linear map. So kernel of a linear map T from V to W is the set kernel of T, which is defined to be all elements of V which get mapped to 0. Another important space. So this is a subspace of V, by the way. So there's another problem for you. Prove it's a subspace of V. The image of T from V to W is, we'll call it T of V, and this is exactly what it sounds like. It's the set of all W and W such that W is equal to T of V for some V. And this thing is a subspace of W. Okay, so a nice property, well, there are two nice properties. One of them is obvious. So it's clear that T is surjective when T of V is equal to the entirety of W, right? Because that means that every single element of W is mapped to by something, by T. How do I say this? Every element of W is mapped to from some element in V using T. And that's the definition of surjective. So that one's pretty clear. What's less clear is that T is injective if and only if the kernel of T is 0. So this is a nice property. Proof is not hard, but since I'm running low on time, maybe I'll skip that one. So this is a nice problem. Okay, maybe after we're done, if any of you want to see that, then we can do it. So a really nice result is what's called the first isomorphism theorem. Which says that if V is, let me be a vector space, and let T be a linear map. So whenever I want something to be a linear map from now on, I'm just going to put a little tilde here, and that'll mean linear. Okay, then first isomorphism theorem tells us that V modulo the kernel of T is isomorphic to the image of V. So there's also a first isomorphism theorem for groups. There's one for rings and so on. I think that this is worth doing. Okay, I'm going to go ahead and do it. Okay, so first recall what this thing means. V mod kernel of T. This is the set of all left cosets of the kernel. Okay. And this thing is in fact a vector space itself, right? So it's an abelian group where the addition is defined as V plus kernel of T plus U plus kernel of T is V plus U plus kernel T. Okay. So that's how we define the addition, and the scalar multiplication is defined similarly. So K times V plus kernel of T is k times v plus kernel t. Right? And you can show this thing satisfies all the properties of a vector space. I won't go that much in detail, but all you're doing is checking down a list, so not hard to do. But anyway, we can define a map phi, which takes v modulo the kernel to the image of v. And the way we define it is by phi of v plus kernel t, right? This is an element of this space. Is just going to be equal to t of v. Okay. And you can argue with me at this point. How do I know that this map is well defined, right? How do I know if v plus kernel of t is equal to u plus kernel of t, right? That's totally possible. How do we know that phi of v plus kernel of t is equal to phi of u plus kernel of t? So in other words, how do I know that this thing actually is a map, right? Two things that are equivalent to each other actually get mapped to the same thing. Well, if these two things are equivalent, then that means that, let me be really precise. That means that v minus u plus the kernel of t is equal to 0 plus the kernel of t. Okay. So I subtract the u over, and I get v minus u here. And on the right-hand side, I get 0 plus kernel t, which is just the, as a set, it's just the kernel of t, right? Okay, so that means that v minus u plus some element of the kernel, let's call it w, is equal to 0 for some w in the kernel of t. So, i.e., u is equal to v plus w. Well then, phi of v plus the kernel is equal to, oh, sorry, I want to do u. Phi of u plus the kernel is equal to, by definition, this is t of u, but t of u is t of v plus w, which is t of v plus t of w by the linearity of t. But w is in the kernel of t, and so this thing is 0. And so we're left with t of v, which is, by definition, phi of v plus the kernel of t. And so, indeed, if u plus kernel of t is equal to v plus kernel of t, then they get mapped to the same thing. So we do have a well-defined function. We're not cheating here. Okay. So now we have to check a few things. We need to check linearity, and we need to check that this thing is bijection. So for linearity, let k be in the underlying field, then phi of k times v plus the kernel. So this is just some arbitrary element of our space v modulo the kernel. Well, this thing by definition is t of kv, right? Because this is kv plus kernel. And t is linear, so we get k of tv. And this thing is k times phi of v plus the kernel. Okay, so we get that property B of linearity. Now we need the homomorphism property, and that follows similarly. So to save some time, let me skip that one. But it's also true that t of u plus kernel of t oops, plus v plus kernel of t is equal to t, that should be a phi of u plus kernel t plus phi of v plus kernel t. Okay, so this is also true, and it follows from the linearity of t, just like it did for the property where you pull out the scalar. Was it homogeneity, I think. Okay, so phi is linear. Where we go from there? We also have to show that's bijective. And we can use the proposition I had before. Okay, so we can show that. Yes, okay. So surjectivity should be pretty clear. So phi of v mod the kernel of t, that's definitely equal to the image of v, right? T of v, right? Because how is this defined? Well, it's defined by sending v plus kernel of t to t of v. Right? So how do I get any old element of t of v here? Well, I just map it with, I just map the element v plus kernel of t on the left-hand side over to the right-hand side. So surjectivity is immediate. Right. Injectivity, suppose phi of v plus kernel of t is equal to 0, right? And we're going to use that proposition that tells us that when the kernel is equal to 0, then phi is injective. So this implies that t of v is equal to 0, which implies that v is in the kernel of t. And if v is in the kernel of t, that implies that, well, kernel of t is a subspace, right? So if I add, if v is inside of it already, then v plus kernel of t is just the kernel of t. Written another way, it's 0 plus kernel of t, right? And this is the identity element of v mod kernel of t. And so that implies that v plus, no, this is what I wanted. Okay. That implies that the kernel of phi is equal to just the element 0 plus kernel of t. And so that implies that phi is injective. Okay, so all that was just to say this very nice result that if you have a linear map from t from v to w, then if you find the kernel and you mod out v by the kernel, this is isomorphic to the image of that map t. Okay. All right. Oh, God. So the last thing I think I want to talk about today is just this really important concept introduced in that last section of chapter 2 in Steinberg. We'll see this come up in the representation theory itself. Okay, so this is a another group here. Actually, it's a ring, but this is the endomorphisms of V, which is another way of saying linear maps from V to itself. A little tilde there. Okay, so let X be a subset of all the linear maps from V to itself. And let W be a subspace of V. Then W is called X invariant. If for any A in X and any W in W, one has that A W is still in W. So in other words, if you take the entire set X and act on the entire set W, it's still contained in W. Okay, so a key example of this is the eigenvalue problem. So if you take a linear operator, you find its eigenvectors and its eigenvalues, then the set of eigenvectors forms a subspace, set of eigenvectors of a particular, associated to a particular eigenvalue, so forms a subspace called an eigenspace. And that eigenspace is invariant under the action of your original operator. Okay, so I originally wanted to say something about that, but I'll leave it there. And yeah, okay. So we'll pick it up next time. There's a lot in that chapter 2 of Steinberg that I wasn't able to touch on today. It's because there's so much condensed into like 4 or 5 pages. But that's okay. Any questions? So next time we're going to talk about representations of groups, finally. So we'll leave it there.